Imagine drinking a cup of milk that looks normal, tastes normal, and even passes all the protein tests in the lab, but still ends up sending babies to the hospital. That actually happened in China in 2008, when a milk powder scandal caused hundreds of thousands of infants to fall sick. The problem wasn't what the milk looked like on the outside, it was what it was made of on the inside. In this lesson, we're going to zoom in and see how the chemical composition of a substance can make the difference between safe and deadly. By the end, you'll understand why learning about elements and particles is not just for exams, but also for real-world safety. Let's start with the story behind that scandal. In 2008, some milk powder manufacturers in China secretly added a chemical called melamine into baby formula. Melamine is normally used to make hard plastic plates and bowls, not food. It has a lot of nitrogen in it, and protein tests in the lab actually measure nitrogen to estimate how much protein is present. By adding melamine, the milk powder cheated the tests and looked like it had more protein than it really did. But inside babies' bodies, melamine formed crystals and damaged their kidneys. About 300,000 children were affected, around 54,000 were hospitalized, and at least 6 babies died. This shows how dangerous it can be when the chemical composition of food is changed just to pass a test. So why are we spending time in Sec 1 science learning about chemical composition? Chemical composition simply means what a substance is built from at the particle level. Which atoms are inside, how many, and how they are arranged. This hidden structure decides many important properties, like whether something is safe to eat, whether it conducts electricity, and whether it is hard or soft. For food and medicine, knowing the composition tells us if harmful substances are present, like melamine in the milk. For materials like metals and plastics, composition helps us choose the right material for buildings, wires, or tools. Even our own bodies depend on the correct chemical composition to function properly. Now, let's look at a simple example you see almost every day, an ice cube. When you look at an ice cube with your eyes, it just seems like a clear, solid block of frozen water. But if we could zoom in millions of times, we would see that the ice is actually made up of a huge number of water molecules arranged in a regular pattern. Each water molecule is moving a little bit, even in the solid state, but overall they are locked into position to form the solid. So even something as ordinary as an ice cube has a very specific structure at the microscopic level. That structure and composition are what give ice its properties, like being solid and cold at low temperatures. Now, we can define chemical composition more clearly. Chemical composition is the types, arrangement, and ratio of atoms that make up a substance. For example, water has the formula H2O, which means each water molecule contains 2 hydrogen atoms and 1 oxygen atom joined together. Oxygen gas has the formula O2, meaning each molecule has 2 oxygen atoms joined together and no hydrogen at all. Even though both formulas use the letter O, the number of each type of atom is different, so the substances behave very differently. So when we talk about composition, we are really talking about how many of each kind of atom are present and how they are combined. Let's compare H2O and O2 more directly. Both names contain the letter O for oxygen, but H2O is liquid water and O2 is the colorless gas that we breathe in. Water is made of hydrogen and oxygen atoms, while oxygen gas is made of only oxygen atoms. Because the composition is different, water is a liquid at room temperature, can be drunk, and has a certain boiling and freezing point. Oxygen gas, on the other hand, is a gas at room temperature and supports burning, but is not something we drink. This shows that just changing which atoms are present, or how many there are, creates a completely different substance. In this topic, we classify matter based on its chemical composition into 3 big groups. First, we have elements, which are the simplest form of matter, and cannot be broken down into simpler substances by chemical means. Second, we have compounds, which are substances made when atoms of different elements are chemically combined in fixed ratios, like water or carbon dioxide. Third, we have mixtures, which contain two or more substances mixed together, but not chemically joined, like air or salt water. In this video, we'll focus on understanding elements clearly, because they are the basic building blocks for compounds and mixtures. Let's define an element more carefully. An element is a pure substance that is made up of only one type of atom. It is the simplest form of matter, and you cannot break it down into a simpler substance by heating it or passing electricity through it. For example, if you heat a piece of pure copper, it might melt or change state, but it will still be copper. That's because the atoms themselves are still copper atoms. So when you hear the word element, think one type of atom, and cannot be broken into something simpler by chemical methods. One way to imagine elements is to think of Lego bricks. A single Lego brick on its own doesn't look very interesting, but you can combine many bricks in different ways to build houses, cars, or robots. Elements are like the Lego bricks of the universe. An element such as iron, oxygen, or carbon is one brick type. When these different elements join together in various combinations, they form all the substances you see around you, from water and air to plastics and metal. If you understand your bricks well, it becomes easier to understand the bigger structures built from them. Elements are not only found in rocks and metals, they are also found in your own body. For example, the elements carbon, hydrogen, oxygen, and nitrogen make up a large part of our bodies. Plants and animals are also built from these and other elements. Non-living objects, like steel beams in buildings, glass windows, and plastic bottles, are also made from elements combined in different ways. So whether something is living or non-living, its structure still depends on which elements are present and how they are arranged. Now we need two very important words, atom and molecule. Atom is the smallest particle of an element that still has the properties of that element. A molecule is a group of two or more atoms joined together. For example, oxygen gas is made of O2 molecules, where two oxygen atoms are joined. Water is made of H2O molecules, where two hydrogen atoms and one oxygen atom are chemically bonded. In this topic, we won't go deep into the internal structure of atoms yet, but we need to know that atoms combine to form molecules, and molecules combine to form the substances we see. Let's take a very common object, an iron nail. When you pick up an iron nail, it feels solid, heavy, and metallic. But if we zoom in at the microscopic level, the nail is made up of a huge number of tiny iron atoms packed together in a regular pattern. Every single atom inside that pure iron nail is the same type of atom, the element iron with the symbol Fe. This is a good example of an element in the solid form that you can see and touch easily in daily life. All the known elements are organized in a big chart called the periodic table. Right now, scientists have discovered about 118 different elements. Each element has its own name and symbol, like hydrogen, H oxygen, O sodium, Na, and so on. The periodic table might look intimidating at first because it is full of boxes and numbers, but you do not need to memorize every element. In exams, a copy of the periodic table is usually provided as a data sheet for you to refer to, so your job is to know how to read it and use it. The periodic table is not arranged randomly. The elements are placed in order of increasing proton number, which is also called the atomic number. This means if you move from left to right and from top to bottom, the proton number increases. The vertical columns are called groups, and they are numbered from 1 to 18. The horizontal rows are called periods, and they are numbered from 1 to 7. Knowing which group and period an element belongs to can tell you a lot about its properties. If you look carefully, you'll notice a zigzag staircase line on the periodic table. This line roughly separates metals on the left from non-metals on the right. Elements to the left of the staircase are mostly metals, like sodium, magnesium, and iron. Elements to the right, such as oxygen, nitrogen, and chlorine, are mostly non-metals. Elements that sit along the staircase line, like silicon and germanium, are called metalloids and have properties of both metals and non-metals. This simple pattern helps us quickly classify an element just by its position. Each element is represented by a chemical symbol, usually made of 1 or 2 letters. If the symbol has 1 letter, it is always a capital letter, for example, K for potassium or C for carbon dioxide. If the symbol has 2 letters, the first letter is capital and the second letter is lowercase, like Na for sodium, A for calcium, or Q for copper. Some symbols come from Latin names, which is why potassium is K from kalium and sodium is Na from natrium. In exams, you must write the symbols correctly. Writing Ke instead of Ka is considered wrong. Each box in the periodic table gives several key pieces of information about that element. The most prominent is the chemical symbol, such as K for calcium. You will also see the element's name printed nearby. There is a smaller whole number called the proton number or atomic number, which tells you how many protons are in each atom. There is also a larger number called the mass number or nucleon number, which relates to the total number of protons and neutrons in the atom. The proton number is unique for each element, like an identification number, so no 2 different elements share the same proton number. Now, let's see what groups and periods tell us. A group is a vertical column of elements that have similar chemical properties. For example, the group 1 metals, also called alkali metals, such as lithium, sodium, and potassium, all react vigorously with water in a similar way. A period is a horizontal row of elements. As you move from left to right across a period, you see a gradual change in physical properties, such as melting point and conductivity. So that the periodic table is organized to show patterns in both chemical and physical behavior. Let's compare metals and non-metals based on their appearance and state at room temperature. Metals are usually shiny, especially when freshly cut or polished, and most of them are solids at around 25 degrees Celsius. There is one famous exception, mercury, a metal that is a liquid at room temperature. Non-metals, however, are often dull in appearance when solid, like sulfur or carbon in charcoal form. Many non-metals exist as gases or liquids at room temperature, such as oxygen gas and bromine liquid. So just from sight and state, you can often make a good guess whether a substance is a metal or not. Metals and non-metals also differ in other important ways. Metals are generally good conductors of heat and electricity, which is why we use metals like copper in electrical wires and aluminum in cooking pots. They are malleable, meaning they can be beaten or rolled into different shapes, and ductile, meaning they can be drawn into long wires. Non-metals are usually poor conductors of heat and electricity, which is why materials like plastic and rubber are used as insulators. When non-metals are solid, many of them are brittle and break easily if you try to bend them, like a ceramic plate. These contrasting properties are very useful when choosing materials for different purposes. Yeah. Next, let's separate physical properties from chemical properties. Physical properties are qualities you can observe or measure without changing what the substance actually is. Examples include color, melting point, boiling point, mass, density, length, and volume. Chemical properties, on the other hand, can only be observed when the substance undergoes a chemical reaction and its composition changes. For example, how a metal reacts with oxygen acids, bases, or water are all chemical properties. When group 1 metals react violently with water, forming new substances, we are seeing their chemical behavior, not just a physical change. Let's look more closely at the group 1 metals reaction with water. How? If you drop a small piece of sodium into water in a controlled lab setting, you will see it fizz, move quickly on the surface, and sometimes even catch fire. As you go down the group, from lithium to sodium to potassium and beyond, the reactions become more vigorous. Some of the heavier group 1 metals are so reactive that it would be extremely dangerous to put them in water, which is why you won't find videos of francium reacting with water. This shows that elements in the same group share similar chemical properties, but the intensity can increase as you move down the group. Of course, these experiments must only be done by trained adults in a proper lab, not at home. In lower secondary, you do not need to memorize every element, but there are some metallic elements that you will see very often. Sodium, symbol Na, is used in common table salt, sodium chloride. Magnesium, Mg, is used in alloys and was once used in flash photography because it burns with a bright white flame. Potassium, K, is important in our bodies and also found in some fertilizers. Calcium, Sa, is found in our bones and teeth and in limestone and cement. Iron, Fe, is used for building structures and tools, and copper, Cu, is widely used in electrical wiring. Knowing these examples helps you connect the periodic table to real-life objects. Let's test your understanding with a quick question. Ahalo, what is the basic building block of all matter, the simplest form that cannot be broken down further by chemical methods? Is it A, a compound, B, an element, C, a solution, or D, a suspension? Pause the video now, look at the options, and pick the one you think is correct. When you are ready, unpause to check your answer. Correct answer is B, element. An element is a pure substance made of only one type of atom, and it cannot be broken down into a simpler substance by chemical means. Compounds and mixtures are built from elements, not the other way around. No? So you can think of elements as the smallest Lego bricks, and compounds and mixtures as the bigger structures built from those bricks. As long as you remember this idea, many later topics in chemistry will make much more sense. Here's another question, this time about metals and nonmetals. At room temperature, which statement is true? A. All metals and nonmetals are liquids or gases. B. All metals and nonmetals are solids. C. Most metals are liquids or gases, and most nonmetals are solids. D. Most metals are solids, and most nonmetals are liquids or gases. Pause the video and think about what you have learned about their states at room temperature. When you have chosen an answer, unpause to see the explanation. The correct answer is D. Most metals are solids, and most nonmetals are liquids or gases at room temperature. For example, iron, copper, and aluminum are metals that exist as solids at around 25 degrees Celsius. Mercury is the only common exception, because it is a liquid metal at room temperature. Many nonmetals, like oxygen and nitrogen, are gases at room temperature, and bromine is a liquid nonmetal. Of course, some nonmetals, such as carbon and sulfur, are solids, but overall, we see that metals are mainly solids, while nonmetals often appear as liquids or gases. Let's recap the main points from this lesson. To review. Elements are pure substances made up of only one type of atom, and are the simplest building blocks of matter. All known elements are organized in the periodic table in order of increasing proton number. A zigzag staircase line on the table roughly separates metals on the left from nonmetals on the right, with metalloids sitting along the line. Metals are generally shiny, solid, good conductors, malleable and ductile. while nonmetals are often dull, poor conductors, and maybe gases or brittle solids. Understanding these patterns will help you a lot in future chemistry topics. You might be wondering how all this helps you beyond tests. Knowing about elements and their properties helps engineers choose the right materials for buildings, bridges, and electrical system. It also helps scientists and health authorities check whether ingredients in food or medicine are safe and detect harmful substances like melamine. For you as a Sec 1 student, this topic builds the foundation for deeper chemistry in Sec 3 and beyond, where you will study atoms, molecules, and chemical reactions in more detail. The better your foundation now, the easier those future topics will feel. To strengthen what you've learned, here are some practical next steps. First, practice reading the periodic table. Identify the symbol, group, and period of common elements. Second, start to memorize the names and symbols of key elements like HON, C, Na, Mg, K, CaFa, and Q, because they will appear again and again. Third, try more questions that ask you to classify substances, elements, compounds, or mixtures, and to compare metals and nonmetals. In the next lesson, we will build on this by looking more closely at compounds and mixtures, so that you can see how different elements combine to form the substances around you.